This lesson is an introduction to circles, a lot of vocabulary, and some information about tangent lines. So first of all, here's your circle, and you've got your center here, of course. A radius is any segment that goes from the center to the edge, so all radii are the same length. Here's two radii, one this way, one this way. Together you get a diameter. A diameter is a chord that goes through the center. It's the longest chord. A chord, in general, is any segment that connects 2 points on a circle. And so as I move this around, it's a chord the whole time because the two endpoints are always on the circle, and you see it gets its longest as it goes through the center. Now it's a diameter, and now it's just, well, any old chord. A secant can be thought of as an extension of a chord. So a secant is a line that cuts through 2 points on a circle. Here you have a tangent. A tangent touches a circle in exactly 1 point. And a tangent and a radii, when they touch here at what's called a point of tangency, then they always form a right angle. So this is a right angle here. This is a right angle over here. See, as I move that around, it's always a right angle. And we have here what's called an intercepted arc. That's an intercepted arc. So here's a central angle because it has as its vertex on the center, and it intercepts this intercepted arc. Now we have inscribed and circumscribed. This polygon, this pentagon here, is inscribed in the circle, or you could say the circle is circumscribed about the pentagon. This circle is inscribed in the octagon, or the octagon is circumscribed about the circle. Now, tangent segments. Okay, these are called tangent segments. They're not tangents because tangents are lines they go on forever and ever. And the idea here is that tangent segments that go into the same point are always the same length. So I can move this point around, and you see it moves the intersection point, but those tangent segments are always the same length. No matter how I move these points around, as long as they are indeed points of tangency going to that same point M, then the tangent segments will be the same length. And then the other major piece here is this idea that if you have a radius and you have a chord and they are at right angles to each other, then that means the radius must be bisecting the chord, and therefore this intercepted arc is split into two congruent pieces, the blue and the red. You see the blue and the red are the same measure. Conversely, if the radius cuts the chord in half, therefore you get a right triangle. And so move this around a little bit. You see these are always the same measure. They're always exactly half of the entire thing. A, B, and BC are always the same amount, no matter how I move this around. Okay, now because we get right triangles, or excuse me, because we get right angles when we have this situation with a radius bisecting the chord, and also when we have radii and tangent lines, we have right angles. Because of that, we're going to get right triangles. And just to remind you, with right triangles comes things like Pythagorean theorem, knowing your Pythagorean triples. Also 30-60-90 ratios, 45-45-90 ratios, and then, in addition to that, SOHCAHTOA, so some basic right triangle trigonometry. So now some examples. Okay, over here we have a radius and a tangent line, which implies this is a right angle. So in this triangle there's 180 degrees. So to get angle x, you do 180 minus 90 minus 58, which is equal then to 32 degrees. Over here, because this is a tangent line over here, and these are as a radius, this will be a right angle, this will be a right angle. In any quadrilateral, there's 360 degrees, so 360 minus 130 minus 90 minus 90, and that's going to be then 50 degrees for x. And then for this problem, all these lengths will be the same, and so there's 360 degrees around any point, so that angle will be 360 divided by 5, which will be 72 degrees. Okay, over here, again, we've got a radius and a tangent, so therefore this is a right angle. So now we can use Pythagorean theorem. We can say a squared, which is going to be this x here, plus b squared, so 8 squared, is equal to c squared, which is x plus 2 quantity squared. So this becomes x squared plus 64 is equal to x squared plus 4x plus 4. Remember to write this out as x plus 2 times x plus 2. You see you get the middle term. Cancel these. Subtract 4 from both sides. and so x is equal to 15. For this problem number 5, if this is 3, we know this is also 3 because all radii are the same length, so we can say that x squared plus 3 squared is equal to 10 squared, realizing that your hypotenuse is that length there because your right angle is over here at your point of tangency. So x squared is equal to 100, that's 10 squared, minus 9, which is 3 squared. So x is equal to the square root of 91. And then over here, we know that CB is 9 again because it's a radius. So we can say that 9 squared plus 12 squared, because that's a right angle, is x plus 9 quantity squared. So that's going to be 81 plus 144 x plus 9 squared, 225 x plus 9 squared. A couple ways to do this problem. Easier ways to take the square root of both sides. Plus or minus 15 is x plus 9. So x is plus or minus 15 minus 9, which is 6, or negative 24, which doesn't make any sense. You get x is equal to 6. Okay. This problem, this is sort of the gear problem is the idea. Now the first thing I did was you always have to draw in a line from the center of the smaller circle, which will be perpendicular to this radius. So I added that in already. So that's a right angle. And you do that because then you know that if this is 25, this red segment will also be 25. And if this is 9 over here, we know this piece will be 9 over here, which makes this 3. So now you have yourself a right triangle right in here, where this is your right angle. That's your right angle. And so 3 squared plus 25 squared is x squared, or x squared is equal to 625 plus 9, which is 634. So whatever the square root of 634 is, would be x. Okay, now it's just a little definitional stuff. The polygon is, well, it's outside, so it's circumscribed about the circle. Here it's inside, so it's inscribed. Here it is outside, so it's circumscribed. So we got circumscribed, inscribed, and circumscribed. Now a couple problems based on this idea of tangent segments being equal. So if this is 5 from this point over to here, we know that this must be 5 as well. And if this is 4, we know that this must be 4 as well. And if this is 3, we know this must be 3. The point was to find the perimeter. And so you basically add up 5, 5, 3, 3, 4, 4, and you get 24 centimeters. A couple more like that. Over here, if this piece is 6, we know this is 6. This is sort of working your way around. If that's 6, we know this is 3, because it has to be 9 together. If that's 3, this must be 3, because they're same point of tangency. Same tangent segment. If that's 3 and this is 8, this must be 5. And if that's 5, we know this is 5. So we work our way all the way around the circle, and then you add 5, 6, 6, 3, 3, and 5 to get your perimeter. Same thing over here. We have to work our way all the way around the circle. So this is 5, which makes this piece 5. Subtract it from 12, which gives you 7 here. That gives you 7 over here because the tangent segments are congruent. This will be 4 because you subtract from 11. This will be 4 since tangent segments will be the same length. And then, we know that's 6. So if that's 6, this piece will be 6, which makes this 4 because 10 minus 6 is 4. And if that's 4, then this is 4. So we got 4 and 5 and 5 and 7, 7, 4, 4, 6, 6, and 4, and just add the whole thing up. And actually, the chord radius that I previewed, that's going to come up a little bit in the next section when you have situations where, again, you have right triangles. So it's going to be 30, 60, 90 we'll see, and SOHCAHTOA a little bit, and also here we have some Pythagorean theorem.